Okay, I'm recording, and let's take a look at Fraunhofer diffraction. And the point of this little paper is just to say, when you're doing Fraunhofer diffraction of a slit, it's the same thing as the Fourier transform. You're essentially taking a Fourier transform of this slit when you look at the answer on the wall that's distant from there. So this is just a little mathematical proof of that fact. Let's begin by assuming that the slit has some transmission function. So you've got some f, so x will be the variable up and down in the slit here. And f of x tells us how much light gets through at that point. And so for a simple slit, you might just have f of x being 1 over a certain space of x and 0 everywhere else. That'd be a simple kind of a slit. If you had a multiple slit, you'd have several places where it was 0, or 1, I should say. 1 would be transmitting, 0 would be not transmitting. So it just tells you how strong the scattering field is out here from that particular point in the slit. Now, if you try to work out what the electric field is going to be, it's going to be an integral. You're going to have to integrate over this whole slit. You're going to have to add up the components from each little tiny piece. And so here is one little piece. So here we're looking at what is the electric field at some angle from some little piece of it down here. And we did this kind of thing before. I'm just doing it in a little bit more general way here. And so that little bit of electric field dE, it's going to have some amplitude on it, just that tells you what you get if everything comes through. And then here is this the slit transmission function, this f of x that I've just been talking about. That would just simply multiply whatever's coming through. And then the rest of this is the usual phase factor. And here it even includes the phase as the phase would change as you get further away, as you go in R. That we usually don't bother about. What we care about is how the phase changes with x and sine theta. X being where we are in the slit, and theta being what angle we're looking at on our screen out there. So you put that all together and then integrate. So here it is. I've started to do the integral. And so f of x has to stay inside because we're integrating over x, over the whole distance along this slit system or whatever it is. But the e to the ikr, those are all constants as far as the integral goes, and so that can come out in front, and in fact we'll ignore it in a minute. That's just a phase factor on the distant wall. The further away the wall is, the bigger the phase factor is, but it's the same for all the points, so we just sort of leave it out. What we care about is the difference from one point to another, and that is in this e to the ikx sine theta. That part we have to keep inside the integral. And if we're going to make this general, we want to consider slits that could be quite large, and so we'll integrate minus infinity to infinity, if you like, as big a slit as you want. So now, simplifying this, let's ignore the phase factor, and while we're at it, let's ignore the amplitude out in front. Just call it 1. Normalize everything to 1, and then we just don't have to bother about that. So at the perfect center of your diffraction pattern, you'd have an intensity of 1. Well, electric field of 1, and an intensity, I guess, also of 1. And now we'll make a change a variable. Instead of integrating over x, let's sort of rescale things. Well, we'll still integrate over x, but let us rescale the function along the wall. Instead of doing it as a function of theta, or we could do it as a function of some distance up and down on the wall, Let's do it as a function of k prime, where k prime is just k times sine of theta. So as you move up and down in different thetas, you'd have different k primes, is what I mean by that. Then, when you make that substitution, am I running off the page? Looks like I am. There we go. You end up with this result. Now, which of you have done Fourier transforms before? Have you guys looked at Fourier transforms? Okay, 2 of you have, 2 of you haven't. Yeah. So if you've seen Fourier transforms before, you say, oh yeah, that looks like the formula for a Fourier transform. Now, Fourier transforms can be written a whole lot of different ways. They can be written with an exponential in complex form like this, or they can be written in terms of sines and cosines. But the point, and whether you've got where the 2 pi's are, I'm not sure where the 2 pi's got in this formula. That's interesting. They're gone. I don't know if they're swallowed up in my k prime somehow. Oh, yeah, it has to do with the inverse transform. You also have an inverse transform that gets you back again. And if you don't have them in this formula, you usually have them in the inverse formula. So that's why they don't happen to appear here. But what you do in a Fourier transform is you take a function of a variable like x, and you transform it into a new function of a new variable. And I like to think of it in terms of going from time to frequency. That's the one that's most familiar to me. But that's very much what this is like. In this case, we're going from a spatial variable, a function that's varying in space. And then what we're finding over here is a function that tells us the periodicities of that first function. Ways in which it is periodic show up in this function. So we're finding spatial frequencies in a sense. Here is a kind of drawing to relate these perhaps. So maybe here is a slit that's got a whole bunch, well, it's a multiple slit. So here it transmits, here it doesn't. Here it transmits, here it doesn't, and so on like that. And let's imagine that this is a whole bunch of slits, essentially, in a row. Then when you perform this either Fourier transform or do the experiment, either one, what you get is a diffraction pattern or the Fourier transform. They are the same thing. They are one and the same. With, I guess, the one caveat that if you're looking at the diffraction pattern, you're seeing intensity, and the Fourier transform is just the electric field. So you'd have to square the Fourier transform to get the intensity. But it gives all the same ideas, and one of these peaks that corresponds to, in a sense, a fringe in the diffraction pattern is related to a periodicity back in the original slit transmission function. So this peak here represents the basic periodicity of this function. And the fact that there's another one at twice that frequency is related to the fact that these are narrow peaks. If you could build a slit, I don't know how you would do this, but if you could make one that had a perfectly sinusoidal variation, so it went sinusoidally back and forth between 1 and 0, then you should get a diffraction pattern that just has one peak, because the Fourier transform of a single sine wave is just one frequency. And you wouldn't have these higher frequencies, which are like harmonics. They essentially are the harmonics. But when you have a slit function that has sharper components in it like that, then that generates more of these harmonics. And in fact, the narrower you make the slits, the individual slits, the wider is the pattern here, the further these go. These will be the same intensity way on out. Anyhow, it's just kind of a basic fact. It's sort of a profound thing in a way that when you're looking at diffraction patterns, you're essentially looking at the Fourier transform of the thing you're diffracting from. At least if you are in the far field, in the Fraunhofer case. In the near field, it's much more complicated than that. And we'll look at that in just a moment. Do you have questions on this before we move on?
I'm not quite sure I'm understanding how the diffraction pattern is correlated to the slit transmission. Like how we get 3 peaks out of 4.
Oh, it's not just 3. They keep going.
Oh, okay.
Those keep on going. I should have drawn more and more of them. They keep on going. And these would probably, in most situations, they would decrease in amplitude after a while. And that depends on the details of the shape of this function back here. And so, like I say, if you have a real narrow slit, then these stay high for a long time. The same as if you take the Fourier transform of, well, if you have a waveform that is just on and off, a little buzz like this, that just, that has harmonics that go on forever. It has a lot of high harmonics, and the same thing is true here. On the other hand, if you widen this out, in fact, if you made this a perfect square wave with 50% duty cycle, then the second one here would be absent. There'd be a third one that would be present, much lower than the first, and the fifth one, or the fourth one, would be absent. All the even ones would be gone. It's just Fourier transforms again. The Fourier transform as square wave has only odd harmonics present in it. That sort of thing would be going on. This, at one point, this was actually done. People used optics to do Fourier transforms. It was a way of carrying out a Fourier transform. And in fact, Hecht has a little bit on that in one of the chapters. You can look at it. These days, nobody does it that way anymore. It's far better to take whatever thing you've got and put it in a computer and take the Fourier transform that way than to try to carry it out with an optical system. It just doesn't make any sense to try it that way. But that was actually done at one time. Any other questions? I'm not sure we're going to do a whole lot with this, but I wanted you to be aware of it. Okay, let's move on to this next section that is going to be a little difficult. This is in Hecht. It's dense. This chapter that we're in has an awful lot of math. I guess a lot of them do, but this one does as well. And some of it's kind of hard to follow. But this section, I think you can understand, and it leads to some really useful, well, both concepts and actual applications. So what we're going to be doing is looking at circular apertures. And we're going to be talking this time about the Fresnel case rather than the Fraunhofer case, which is to say we're not going to assume that we're at some great distance. So we'll imagine that we have a source that's not so far away from a slit that is circularly symmetric. So we're going to be analyzing this in terms of rings, essentially. And we'll be comparing the straight through path right through the direct center to a point out here, which again isn't infinitely far away. And we'll compare that path with the path through a ring. So imagine that this was an annular opening in here. A ring-shaped opening would be a little difficult to construct. You'd have to have a transparent material or something. But imagine that the path through one place in this opening that gets you back. You have to change direction in there at some point, and we'll be using the same Huygens idea that that along the way you just simply regard the wave that proceeds to the final point as well, how to say this? You start with the wave spreading out, and then it meets the slit, and then each point on the wave becomes the source for a new wave that heads on. That's sort of Huygens' principle. And Fresnel added a key point to it that we'll get to in a little bit, I believe. If we look at the path of a ray that's passing through some point here, that's a distance away from the center line. The center line is the path that just goes straight through and doesn't need to bend. So we'll consider that this thing has an optical axis, and our source and our receiving or listening or looking point are both right on the optical axis for this analysis. And we'd like to compare this direct path with this alternate path that's some distance r, capital R, from the center. So here's the construction that we end up with. And here is where I'm using exactly the same notation as Hecht. So here's the straight through path, and then this alternate path off to the side, and it's shifted. It's gone through at a place that's a radius capital R sub m. The sub m you can kind of ignore for now. At the very end, you'll see why we put that in there. So on the left are rows, and on the right are r's, little r. So this is a row 0 is the direct path up to the aperture, I guess we'll call it. And then R0 is the direct path on from there. And then rho sub m and R sub m are the other two paths. And we're going to compare these paths.
Are the triangles congruent, or are they?
They are not, because
okay.
The two distances are not necessarily the same.
Okay.
All right, so rho sub m, this is just the Pythagorean relationship. Rho sub m is the hypotenuse up here. That would be the square root of rho sub 0 and R sub m, each of them squared. That should be straightforward, familiar to you. And in a similar fashion, R sub m is a square root of those others. That should all make sense to you so far. At a certain point, this probably won't, but at this point, I think you can still follow. We'll see how far we can get. All right, rewriting this just slightly to factor out rho. So I've got rho 0 out in front, and what's left inside is a 1, and then I had a divide by rho 0 squared inside here. Essentially, I divided, how to think about what did I do? I put a rho 0 out in front and divided by rho 0, and then I took this divide by rho 0, put it inside the square root where it becomes a divided by rho 0 squared. And that eliminates the, well, yeah, that divides out the first term, so it becomes 1, and we're left with it in the second term. Does that all make sense?
Don't you have a square root there? So I am sure what you did is that you take b it's row of 0
This
squared.
row 0.
Yeah, and you put it inside before you got it out because it was multiplied
All right,
by 1 times.
let's back up to here.
No, I understand it, but like you can just take it out since you have the square root.
I will take row 0 over row 0 out in front. Now I'll leave the denominator, the numerator there. The denominator I want to move inside the square root. To do so, I have to square it. When I do that, I've got row 0 squared divided by row 0 squared for this term. That becomes 1. For this term, it's r sub m squared over row 0 squared. Does that make sense? Yeah. Okay. Now, the next thing to do is to expand this thing. And here what I'm doing is using the binomial expansion. This is what physicists always do. It's our favorite expansion, I think. So what's the binomial expansion? Oh goodness, 1 plus x to the power p is the same thing as 1 plus p times x plus higher terms in x squared and x cubed and so on that we always neglect. So where you had something to the power 1/2, now you just multiply it by 1/2. It's that simple. It's wonderful. Now that only works if x is small compared to 1. But go back to what this is. This is r sub m over row 0. R sub m is a distance within our little aperture. And row 0 is the distance to the source. And in all of optics, we're always still going to have these distances be large compared to the dimensions within the optical aperture. And so that meets the limitation of the binomial expansion just fine. We'll never consider a case where that would be large or comparable to 1. So we can get away with that expansion. And just simplifying that a little bit, you can write it in this fashion. Now I'm putting the row 0 back in. So I've got row 0 plus r sub m squared over 2 row 0. And then by the same kind of manipulation, I can change this formula for r sub m into the one that we have right here, just doing the very same thing. Same set of operations. So ultimately, I want to add these two together. I want to get the path length along this longer path and compare that with the shorter path. So let's do that. The extra path, well, you can see what the extra path is because we've got row 0 right here. Row sub m is row 0 plus some extra little piece. So that's the extra path length right there. That's the wonderful business of doing this math, that we've teased out what the extra path length is for each of them. And so if you're adding these together, the total extra path is just these two terms. And that can be written in this other form right here. So the extra path length depends on this r, on how far we are from the center as we pass through the aperture. And it depends on that squared. All right, now comes the key idea here. What we're going to do then is divide the aperture. Remember, we're doing this all in a sort of circularly symmetric way. So we're just considering everything as a function of this radius. That's all we care about, how far you are from the center. And what we would like to do now is divide the whole area of the aperture into zones. And we'll draw a circle that'll outline the first zone within that circle. And that first circle will be when this extra path length is exactly half a wavelength. And what that means is any scattering that goes through within that circle must have a path length difference that's less than half a wavelength. And that's what this M is going to be for. M is going to be essentially the index for which zone we're talking about. Just keep in mind that these are half wavelength zones, not full wavelength zones. So so anywhere up to the radius we would get for M equals 1, everything in that has a phase shift that's less than half a wavelength. And then zone 2 would be from half a wavelength to a full wavelength. And zone 3 from a wavelength to 1.5 wavelengths, and so on. So we find the radii that sort of delineate these zones, R sub m, using this formula we've just worked out that depends on ρ0 and r0. It depends on these two distances, as well as on the wavelength. And here I've just simply inverted the formula, so we have R sub m in terms of the wavelength and then those two distances, ρ0 and r0. You probably can't even read that. You might have to go and look it up in Hecht. Did I do something else with it later? I guess I didn't. Maybe I should read this for you. So R sub m is equal to the square root of all of this. That's what the brackets or braces here are, parentheses. Square root of m times lambda divided by 1 over ρ0 plus 1 over r0. That's what's inside there. Can you guys read that? Just barely. Okay. I'm amazed. This camera's doing a whole lot better. Yeah. Okay. Now, for the special case where you've got incident plane waves. So on the incident side, you had ρ0 was infinity. So that the waves that are coming in are not diverging, they're just plane waves. So for that case, ρ0 goes away because 1 over infinity is 0, so you can neglect that term, and you're just left with 1 over r0 on the denominator, and you can quickly rewrite that. So R sub m is just the square root of m r0 lambda. The important thing to note is that the radius R sub m is proportional to the square root of m. So as you count up in index number, as you count up through the zones, the radius of the zone goes up as the square root of the index. And it turns out that that's true in general, not just for that case, but it's always true. In fact, you can see it back in the other one as well, that it's also the square root of m. So it's always some constant times the square root of m. The constant would depend on these distances. That leads to an interesting discovery about the area of each zone. So let's see if we can figure out about the area of each zone. So the area A sub m for the mth zone, the area of that zone would be pi times r sub m squared minus pi times r sub m minus 1 squared. Well, if you just take this sort of generic formula that's c times the square root of m, then this is going to be pi times c squared times m minus pi times c squared times m minus 1. Remember, we're squaring the square root, so they both go away. So you end up with m here and m minus 1 over there, with the result that m disappears. These two terms, the m's cancel out. The m terms cancel out. And we're left with just pi times c squared, which is a constant. Doesn't depend on m. So the area of the fifth zone is the same as the area of the first zone. They all have the same area. That's the important point of that little discovery there. Each of these zones, remember, these are half wavelength zones. These are zones within which all of the scattering that reaches our analysis point is within a half a wavelength in phase. Okay, now let's leave the math behind and try to think about this graphically a little bit using phasors. So here's a drawing of the first zone. I've shaded in zone 1. Zone 2 would be this next ring out here. And then after that would be zone 3. And maybe I'll shade that again so we can kind of see these. And then here would be zone 4. And oddly, these all have the same area. So they've got to get closer together as they get larger and larger in radius or diameter. They have to get thinner. So each ring gets smaller and smaller, or thinner, I guess I should say. But they have the same area, and the area is largely what determines the strength of the electric field coming from that region. So that has something to do with the electric field. What I'd like to do is think about sort of adding up the electric field just within zone 1. Just within zone 1. Think about that a little bit. Well, it's going to depend. If you try to add up little bits, little contributions from parts of the beam that get scattered from different parts of this aperture, maybe you can realize that at least circularly they're all the same. So if you consider a ring, every part within that ring has the same phase. The scattering from this point and the scattering from that point, anywhere around a ring that's all at the same radius from the center will have the same phase. But what we have to do is add up a bunch of different rings to get the sort of result for this entire zone. Each of those rings is going to give us a little vector in our phasor diagram. Let's let this vector represent just an inner circle here, where there's essentially no phase change. So that's the arrow that just goes straight to the right, straight in the real axis direction, the way we usually do it. Now consider the next ring. Now there's just a little bit of a phase shift. That gives us an arrow that turns a little bit from that to represent that phase shift. You guys have done lots of these, so this should look familiar. Now the only question though is, how big should I make these arrows? How long should they be? Well, by the same token as I just did, it turns out you can subdivide this zone into rings also of equal area. and they will have the same phase shift from one to the next. So we can make a whole bunch of arrows that are the same length, and each of them turns exactly the same amount. You can do that kind of an analysis. Where are we going to get when we get all the way to the edge, to the boundary between zone 1 and zone 2? Can you work that out? If we start with the very inner one being straight to the right, what about the contribution from the very last ring, right along the boundary of zone 1 and zone 2? How much of a phase shift are we going to have? So what direction will that arrow be going?
Will it be going to the left?
Yeah, you think that's shifting a full 180 degrees, because we now have a phase shift of exactly half a wavelength. That's the difference between zone 1 and zone 2, is when we have accumulated half a wavelength of phase shift. So yeah, this diagram is going to go all the way around until we're just halfway around a circle. And so that's what I've shown down here. Zone 1, if we did it instead of with discrete arrows, did a proper integral, it would be a perfect curve. And it would be a semicircle going all the way around and then pointing that way. So that's what represents the total contribution from zone 1. Now remember, this whole analysis is just for what's going on right on the center line. We're not considering what's going out here anywhere. We're still just doing that one point. It turns out we can very quickly broaden this at the end, fortunately. It looks like it would be impossible because you'd lose all your symmetry, but a wonderful thing happens in just a minute. Okay, so that was zone 1 up there. Now, what's the contribution from zone 2? Well, it looks like you would just be circling right back around. And since zone 2 has exactly the same area as zone 1, you'd come right back to 0. Well, you're saved by one weird fact that I'm still a little puzzled about. I don't quite like this, but it turns out that when you do the Huygens construction, there is a kind of paradox in the Huygens construction. Let me just go back to that for a minute here. If you recall, in the Huygens construction, you imagine that a wave is propagating along, and you consider points along here to be the generators of little ripples that add up to create a new wave. And you don't get a wave off to the side because they don't add up in phase in any other direction except straight forward, until you do something weird and block off a bunch of them, and then you get scattering off in other directions. But here's the conundrum. What about backwards? If you were to really take this construction seriously, it means that whenever a wave is propagating like this, it could instantaneously propagate backwards as well. And of course that doesn't happen. You'd have the wave dividing itself infinitely many times as it propagated along. And this is a kind of a puzzle. And to rescue the Huygens construction from this problem, you have to invent a function that says, yes, these all create these little scattering rings, but we have to make a function that tells us that they're stronger in the forward direction and they get weaker in the backwards direction. And so you usually put in some function of theta, and a simple cosine of theta will suffice, so that the forward scattering gets you a 1 out of this. And if you're scattering all the way around in the exact reverse direction, you end up, oh, wait a minute, it's 2 theta. I think I want in the backwards direction to get 0. I think I need to have cosine of 2 theta. This is called the obliquity factor that is just sort of stuck in to fix the model. It makes it match reality, sort of, but we don't really have much to say why it should be a cosine of 2 theta. What about some other function that's 0 in the backwards direction? You can imagine lots of different forms for that. Anyhow, this is a little bit of an unsettling thing, and I don't quite know what to do with it, but Hecht just points it out and starts using it, and, you know, away you go. I guess that's what we do. So for that reason, the obliquity factor, what that means is as you start deviating from the straight through path, you're going to start getting a little bit weaker. You assume that the obliquity factor must be a smooth function and starts to decrease as you increase the angle. Now, the main thing it's got to do is become 0 when you get all the way to 180 degrees, but it's got to decrease smoothly, and so it's got to start dropping off a little bit. What that means is zone 1 and zone 2 may have the same area, but zone 2 is at a little bit of an angle. The scattering coming through zone 2 is having to bend a little more. And so the obliquity factor makes the scattering a little bit weaker in zone 2, even though it has the same total area. And so when you circle back around, you get a function that doesn't quite come to 0. And then, of course, for zone 3, you're going to circle around again and come smaller yet, and it's going to be a kind of a spiral is what you're going to end up with. Here are Hecht's drawings of that spiral. Now which does he call which here? I'm a little bit confused. Oh yeah, S. Okay, S is the source point. And right here is where you consider the aperture. The aperture is some distance away from the source point. And then P is the place we're actually going to look at it using all of this. Over here is this function drawn that cycles around and around and around. Shoot, what is it called? A vibration curve, I think. It's a funny name. Doesn't make much sense. There's no vibrating going on. But
it does say wavefront and corresponding vibration curve.
Yeah, okay, vibration curve. Yeah. Ah, there we are, vibration curve. So this is the vibration curve. I don't know why I would not have named it that way, but somebody did. So this vibration curve is essentially the phasor diagram. That's really what it amounts to. Except that we can use this curve for more situations than you might think. If you just had a small opening here, a circular opening, a hole essentially, a circular hole, then you would just follow this curve around as far as it went, and the resulting intensity out here would just be the straight path from the beginning to the end. So let's say you open this thing up and you've gone through 1.5 zones exactly, so that the radius of the hole you've created here is just 1.5 zones. Remember, we have a formula for the radius of the zone, so you could calculate what that would be. Make your hole that large. Then on this figure, you'd be going around this circle 1.5 times. You wouldn't go all the way through the second zone. So you'd end about here. And then your electric field at that point would be from the start right to the end. And that would tell you how strong it is. So what this suggests is if you make the hole just the right size, you get a pretty strong field. So if you just include just the first zone, you get a real strong result. If you include the first and the second, make the hole a little larger, it'll get dimmer. You'd end up with a result that would hardly have any intensity at all. Then make it larger again, and it'll get bright again. So depending on the size of the hole, or another way to put it is you could vary one of the distances, and you'd see this, this oscillating going on.
I'm assuming that has to be quite small.
Yes,
amounts of change and a quite small
right.
of a hole.
That's right.
Okay.
Everything about this has to be very small for ordinary optics. You don't
okay. So it's like not something we could see with the iris in the lab.
Not that way. We can see this in the lab. And in fact, you already did. In a minute, I'll get to some, it essentially explains some things that you've been doing already. But it takes a laser and a long distance and still fairly small objects, and then another long distance to where you look at it. Here is a picture of what these zones look like. So for a circular aperture, for particular values of distance, they would look something like this. And you see again, as M gets larger, they get closer and closer together. And here it looks like the odd zones, zone 1 is the middle one. So the odd zones are black, and over here the even zones are black. Now we get to the weird part. This is where it starts getting confusing, because we can still use this even when we're off axis. That's the challenge, to use this same analysis when we're off axis. So let's see if we can understand this figure right here. It's in the text. If you can understand this, then you're home free in this stuff. So imagine, again, we've got a circular aperture, and this is an aperture that happens to be just large enough to encompass two zones, the first and the second zones. That's the picture that's drawn right here. So now we've got the aperture, the square thing, drawn on top of the sort of zone figure where this is just gray instead of being black. Does that make sense to you? So I've taken this aperture and superimposed it on top of a diagram that shows the zones, and we're just seeing zone 1 and zone 2. Zone 1 is black, zone 2 is white. And because those two are the same area, and because of all this cancellation, you're not going to see much. And this corresponds to this first P over here. If you're sitting right at that point, then you're right on the axis of symmetry, and this is the correct diagram. And you wouldn't expect much intensity there, because these two zones are out of phase with each other. Now let's move a little bit. Let's move off axis to point P1. Now, if we've moved over a little bit, remember the zones depend on the axis from the source to the place we're looking. And so those zones are going to come with us as we move, but the aperture is going to stay where it was. And so we're sitting now at P1, and the zones are still lined up, centered on O1 back here. But now the aperture isn't centered on O1. It's centered off to the right a little bit. Now, what has happened in here? Once we've shifted off from O, remember in this first picture, these two were essentially equal in area, and so they were canceling out because they're out of phase. what's going on now? Well, we lost some of 2, and we've gained a little bit of 3. So do you see that this perfect balance has been upset? We now have more odd and less even, because we haven't gained any more of the even, but we have gained some odd. And you can keep going as you shift over to P2. We've gained quite a lot more of 3, and we've lost quite a lot of 2, but oh, now we're starting to get a little bit of 4 creeping back in. And so that's going to start to balance things out. Somewhere in here, there'd probably be a peak between these two. You'd reach a maximum, and then it would start balancing out the other way as you start gathering in some of the next zone. And you can see that when you go far enough away, surely this is all going to even out. And you'd end up with just sort of a uniform, not much intensity. But you might first go through some oscillations. And how many oscillations you went through and what they looked like would depend on the size of this initial hole. And in fact, you see that if you'd chosen the right size initial hole, that first point, P, could be bright rather than dim. Had we made the hole just the size of zone 1, you'd expect it to be very bright indeed. And if you make it the size of zones 1, 2, and 3, then you'd expect it to be bright. So depending on the size of the hole, you could have a bright spot there. All right, here is a diagram. I think this comes straight out of Hecht as well, that just shows what happens when you change the size of the hole, or equivalently, you could change one of the distances. And you can see how the very center, first you've got some brightness. And as you make the hole larger and larger, it just kind of grows. But then at a certain point, a dark point happens right at the center. So that's when you've apparently encompassed exactly 2 zones at the very center. Well, 2 zones, yeah, when you're centered, you're just including the 2 zones, and so that becomes a dark point. Go a little bit further, and now we've got a bright point in the center. Does this kind of make sense? It's quite a story. I'm going to stop there. It's time to stop anyhow. I saw ahead and thought, this is going to take the whole time just to get through this. But it's a neat effect. This is a little bit related to the spot that you saw, that bright spot at the center. As you go further and further, you see this bright spot appearing at times and then not appearing at other times. I think when you get large enough, it basically is there all the time. I'm not quite sure why. But anyhow, when you have a really small spot, you can get these weird effects. Oh, yes, there's one more thing that I must talk about before we disappear. Yeah, you can make lenses, oddly, this way. So here was the formula that I was trying to show you that you couldn't read very well for the radius of a particular zone. And that's as a function of ρ0 and r0. Those are the 2 distances between the source and the observation point. Well, interestingly, you can kind of rearrange this. If you just rearrange this and say, hey, let's just take only the odd zones and only allow through the odd zones, then you'll have a particularly bright contribution at that analysis point we've been using. At that one spot, it will be particularly bright. Not other places, but at that one spot, it will be particularly bright because everything will be in phase. If we use a pattern like this, only somehow make the white part be transparent and the black part opaque, and put that into our beam, then certainly in the direct straight through direction, at that point, we should get a really strong contribution. But at other distances, we won't. At other distances, this will be the wrong pattern. And so the phases won't work out correctly. Well, look at the math of this thing, and you can turn this around and say, if you've picked the radii just right to work for rho and r, you can sort of turn this whole thing around and say, well, what are the distances that work? It turns out there are more than just those two, rho and r, that work for that r. You can imagine if I made rho 0 a little different, I could compensate by changing r0. And you'd get back to the same pattern again. Well, if you rearrange this just a bit, you get to this formula. 1 over rho 0 plus 1 over r0 equals m lambda over r sub m squared. Does this look at all familiar? Just look at that side of it. What does it look like?
The lens maker equation.
Actually, not the lens maker equation, but just the there isn't a name for it, but the object and image distance equation. There's no good name for it. The lens maker one has to do with the radii. But yeah, you're exactly right. And so so you can use these things as lenses. In other words, you put something like this into a beam. So if you have a source from somewhere, a bright source, and it's spreading out, you can put it into a pattern like this and focus it together again. Now, it's strange circumstances in which this is a useful idea. It is used in some weird cases, though. You can buy these things. You can buy Fresnel zone plates. This is from some company, looks like called X-Radia, and they make these things. And they're using them. I think these are for X-ray imaging. So you make yourself a plate like this. There's no simple way to make X-rays refract, but you can make a zone plate and cause them to focus that way. So you simply absorb them. So you make your zone plate with two different materials, one that absorbs the X-rays and the other one that doesn't, and you can focus things together. And there are various other ones. Here are some pictures of them, zone plates. They're typically made very small. These are made for situations where you're trying to do some kind of focusing or whatever in a very small small objects, but they're called zone plates, and they're used for optics. So now you understand that a little bit. And we'll see. I will do some more on rectangular apertures, probably on Friday, when we gather together on Friday. I want to do some on rectangular apertures. And there's another kind of a weird curve that you end up with to analyze those, sort of graphically. And then you can understand from that one why we saw those strange patterns when you stuck objects in the beam. You remember when you put objects in the laser beam and you were looking way down the hall, and you saw this weird, it looked like fringes, but they weren't equally spaced. And so on the edge of a bright object, you saw a sort of intensity that was, what was it? It was dark, and then it came up light, and then it oscillated a little bit. something like that. And we can explain that with another curve, a little bit like the vibratory curve that we just saw. It's a different one. It's called the Cornu spiral, and we'll get to that. But that is, yeah.
Oh, can we meet earlier on Friday, like at 11 or something?
We sure can. Absolutely. I can't meet at 11. I should at least keep that option open for my other class, but I could meet at a different time, either 10, 9, 10, 1.
Yeah.
You don't want to wait until 2.
No, I think because we might go out and walk on the Mississippi River. So
Oh my goodness. Walk on the river.
like near
Along,
it.
I assume you mean. It's not frozen. You can't walk
Oh,
on it.
yeah. Not
Easter's
at
all
this
about
point.
Jesus, John.
Well, I've walked on the Elkhart River many times, but it's been in the middle of winter with friends. But yeah. Okay. Well, how? What should we pick? Would you like 10 o'clock or 9 o'clock? Who wants to?
I would prefer 10 o'clock if we were going to go with either of those times.
Okay.
Yeah, 10 sounds nice.
10 o'clock. Let's meet at 10 o'clock on Friday then, and I think that's when I'll see. Well, we're also meeting tomorrow at. When is that? At 9?
2?
I thought it was at 2.
I thought so too.
No, I don't have it down. Yeah, I don't have it down. I gave you.
We hadn't specifically said anything, but we had on Thursdays we had been meeting at 2. I don't think
Okay.
we had specifically said anything about this week.
Well, it doesn't matter to me. Either one works. 9 o'clock or 2 o'clock. Should we vote on that one? What do you say? 9 or 2?
2.
Yeah, 2's fine.
2.
Two's
Okay.
good.
Thursday at 2. Friday at 10. Okay, and Thursday is 2, and we're going to be looking at those 4 problems that I gave you. Is that right? Okay, so that we'll get through those problems. Should be able to without difficulty.
Can we talk about the quiz on tomorrow as well?
Quiz.
We had a quiz. I was wondering if we could go over that question.
Ah, yes, we did have a quiz. Yes, we will certainly go over that. Absolutely. Shoot, yeah, I gave you a quiz. Where is that thing? Was that a Moodle quiz? Must have been.
Yeah, chapter 9 quiz.
Yeah. Okay. Okay, I will. So, problems and the chapter 9 quiz. You guys keep me in line here. That's great. It's wonderful when you can help me keep my course organized. I've been spending most of my time trying to keep my other course organized, and I depend on you folks to keep me in line here. So,
John, are we gonna have a quiz tomorrow?
I don't think so. I think we'll wait until we've done more of the chapter before. In fact, yeah. No,
Have an exam next week.
we've got an exam coming up. I think that'll be sufficient. I don't
Okay.
think there's need for more. I'm not feeling a need for lots of ways to evaluate you.
So when do you think we're gonna be doing review for the exam?
Well,
Does this mean we only have 2 sessions if we're gonna take one of our sessions before the exam to review?
All right, hang on. Let's see what I've written down. Yeah, so I will finish the material in this chapter essentially on Friday. And then we can go over that on Monday. So there'll be some more problems that I'll have, and we'll go over those on Monday. And then the review for the test would be on Wednesday. The test is on Thursday, and on Friday we can talk a little bit more about projects if you need to, and then the final exam is when you actually give your reports for those. Does that all make sense? That's what I had been planning. Ben.
What day is our final?
Oh, golly. Yeah, shoot, and we're actually going to use it, aren't we? I have it. Oh, this is the wrong place. No, I'd have to look that up. I don't know. Well, wait a minute. Yes, I do.
It's on Thursday from 12 to 2.
Yeah.
Oh, yeah.
Actually, 12 to 2 my time, so it's 1 to 3 Indiana time.
Thursday the
23rd.
23rd, yeah.
Thursday the 23rd from 1 to 3, you say?
Yeah.
Yeah.
Okay.
Nice time.
Yeah, okay. We have to keep that fixed. We can't let that slide around because other classes, well, I don't know. I guess it depends on whether you would have other classes. It's just, I guess, 3 of you that might have other exams that could conflict, but we're being encouraged not to shift those things around willy-nilly just because it'll create problems if we do. In my general physics class, it's going to be an online test, and so I'm just letting people do it all day. But here, since we're reporting to each other, we all have to meet together. So I think we have to use that very time. Okay, that's all I have. Does anybody have anything else you wanted to ask about or talk about?
Are you going to put up on Moodle the previous year's test like we did for the first test to study from?
Oh, I'll do something like that. Yeah, the previous year's test. Yeah, it's an interesting question. It won't be as relevant because I'm not envisioning this test to be that comprehensive.
Okay.
But I'll try to give you some idea of what you're going to be facing. Yeah. I mean, since we're doing this projects instead of the final exam, I'm envisioning that test as being more like a, I don't know, a bigger than normal quiz or something like that, and not trying to do quite as much. I don't see any other way to do it. I can't just have a huge final exam and expect you to do a project and all this stuff at the same time. We've got to, anyhow, so.
John, would you be able to like put those questions before Wednesday so we can solve them? And on Wednesday we would like go over them.
Yeah, so maybe by Monday if I would post, so post test study questions. Is that what you wanted?
That would be helpful.
Yeah, I'll see if I can get those posted on Monday. Then you can work them and we can talk about them again on Wednesday. That might be a good, efficient way to do. Okay. Well, I got it down on my list here of things to do. We'll see. You might want to remind me.
Well.
All right. Well, it's a beautiful day outside here, so I'm going to try to go and have a picnic, I think. Aaron and Ben, you could probably do the same. I don't know about Lucas. What's it like in, where are you, Ohio?
No, I'm just an Elkhart.
Oh, you're just in Elkhart. Oh,
Yeah, it's the exact same.
So it's just Ebtehal. So
Beautiful here too.
yeah, okay. Well, let's all enjoy the weather a little bit, and have a good afternoon. So
You too, John.
see you folks
Bye.
later.
Yeah.